Okay, so for our last type of problem we're going to do in Chapter 10 is we're going to look at matched or paired samples, which is a dependent t-test. Now, in all of the previous examples that we've done so far in this chapter, we've dealt with two different independent samples. And the independent samples meant that if you belonged to one of the test groups, that you actually couldn't belong to the other test group. So what this means now is that we have a dependent example. Now, the dependent example is incredibly important because the main reason for looking at two dependent samples is for the before and the after comparison. Now, it is good to get independent groups if we're trying to see if something has an effect on, one group or the other. And usually the group that doesn't get any kind of impact, or the placebo, if they get anything to kind of make them feel like they've got something going on, that is called the control, and then the other group is called the experimental group. Well, what would happen if it wouldn't be ethical to actually have a control and experiment group? Like, let's say you have a terrible disease and you're trying to figure out a way to cure it. And this way, you would be probably negligent in not allowing for one group to have the possible life-saving treatment. So the before and after really comes into play here, and that would make this one group feel like two groups or two samples. But really what we're doing is we're taking the sample before the treatment and we're taking a sample after the treatment. So it literally is a two-sample test, but we are going to type it in to our calculator as if it was one sample. So there are some general assumptions, though, that first of all, this is random. Second of all, this is dependent. And third of all, the sample is going to be small. And that kind of makes sense just because we're not going to throw a ton of stuff at you in a problem like this. Because what we're going to do is, similar to what we've done before, we have some steps to get through the problem. But the first step, which I like to call step 0, is the actual step of trying to figure out what kind of test we have. And that's actually given in the problem itself. You're going to have a null and an alternative for each of these kind of tests. Whoops, that should be a 0. And I'm using H sub 0 and H sub A for my null and alternative. Okay? Now, the null hypothesis and the alternative hypothesis is a little different in this example than it was in the previous 3. In the previous 3, we had mu sub 1 equal to mu sub 2. But in this case, we are looking at the mu sub d, and the d here stands for the differences. Now, if you have, let's say, a weight loss drug, and you take the weight loss drug, but you don't actually lose any weight, then the weight loss drug did nothing, and the difference between your pre-weight and end weight is actually 0. So in all of these examples, the null hypothesis is mu sub d equals 0, because the null hypothesis is saying, well, the difference is nothing because nothing actually happened with your scientific implementation of whatever it was. Was it a cure? Was it a drug? Was it some kind of exercise intervention? Or what was it? And if the difference is 0, then the null hypothesis is the winner, so to speak. But in the two-tail test, where someone says, was there a difference after the implementation, then you have mu sub d is not 0. It could be plus or minus off of that 0, and the subtraction order then does not matter. So you can subtract it any way you like, and that's going to be either before minus after or after minus before. In the alternative version of the right-tail test, we're hoping that the mu sub d is greater than 0. And in this situation, you always want to subtract the big series of numbers minus the small series of numbers. Now, it might take 1 or 2 tries to get, by the end of the problem, to realize which way was the correct way to subtract if you're trying to force the big minus small direction of this right tail test. If you subtract a certain way and then you see that, shoot, more of my answers were negative than positive, then you got to subtract in the other direction. And you'll actually see this as we actually get into examples. So look at your 2 rows of examples here, or your 2 rows in your test data, and try to figure out which row is bigger than the other row more often than not. And so therefore your left tail test, which is mu sub d is less than 0, we're hoping for more negative numbers than positive numbers. So you'll want to subtract small minus big. And if you have the chance to choose right tail or left tail, please try to choose right tail. More students, in my years of experience working with students in these matched or paired samples examples, do better when they subtract big minus small. But again, always read your problem carefully to figure out if you need a 2-tail, right tail, or left tail test. I have 4 examples. 2 of them you will actually see in this video, but I have 4 examples that actually will cover these possibilities and maybe the best strategies here. Now, the step 1 is not actually like our normal step 1s, which was to do the null and the alternative. This has to be decided before you do anything. The step 1 is to subtract correctly. And what we really mean here is if you chose a right tail test, then you better have mostly positive differences. And if you chose a left tail test, then you should have mostly negative possibilities, or differences, excuse me. Now, step 2 is going to be great because normally this is when we have to run tests to see if we can assume normality, but we are just going to assume normality for all of these examples. Maybe not all of them, just because I do want to show you a situation where we should check for outliers, but for the most part, when you get to your big tests and exams, this is one of those problems where I'll let you assume normality. Just, read the problem and see if it's in the body of the text. Otherwise, you'll do an outlier check. And outlier checks are easy because we actually have the raw data in this situation, which is nice. Okay, step 3. Step 3 is kind of a multi-step here because this is normally when you type everything into the calculator, but we do have to do a little bit of prep work. You have to find the d-bar, and d-bar is an average of the differences. And what's cool about this is that the data setup on the calculator will allow us to do this just by typing everything into list 1. So you're going to enter the differences, not the data, enter the differences into list 1. And if you do that, then the d-bar and also the standard deviation of d, so s sub d, both of these things will be done by the calculator if and only if you enter the differences into list 1, which is why step 1 was to subtract correctly. If you don't actually have your subtraction done correctly, your d-bar and your s sub d, which is your average and standard deviation of the differences, they will not be correct. So finally, we're going to use the t-test. Okay, now this is option 2 on most of your graphing calculators, and we're going to use the data option there since you've typed your differences into list 1. And if you don't want to use the t-test or the data, you can use the one variable stats. And I'm not writing this down in your notes because this would just be reinventing the wheel. You could use the one variable stats and kind of like look through and type everything in stats form instead of data form. Well, steps 4 and 5 should be familiar territory because just like all the other problems that we've done since chapter 9, this is going to be drawing a picture. And step 5 is to make a summary with the inequality, which goes a little bit beyond what the book has you do, but I really need you to compare the p-value versus the alpha just so you have let me know what the actual why you chose what you did. Okay, so for the first of two examples here, we're going to look at our cholesterol data before and after some cholesterol medication. So here's a data from a normal population. All right, by having said that this is from a normal population, that means step 2 is going to be assuming normality. Okay, so step 0 is really looking at what kind of hypothesis test do we have. Now, mu sub d is equal to 0 is telling us, all right, the drug doesn't work. The difference before and after wasn't strong enough to tell me if there was a significant difference. And look, that sentence right here can be concluded that there is a significant difference. This is the alternative hypothesis that says mu sub d is not 0. So what this means is that subtraction doesn't actually matter. You can subtract these numbers any way you want. You can subtract before minus after, or after minus before. So now in step 1, we're going to subtract, and let's go before minus after. And again, since it doesn't matter, I could have chosen after minus before. And this is when books, I think, sometimes get into trouble by forcing students to do things a certain way, because it is an easier, I think sometimes the rigidity of a process can actually make things harder for you. So let's go and subtract. 210 minus 190 is 20. And then 235 minus 170 is 65. So these are some pretty good drops. This is a drop of 20 points of cholesterol, 65 points. But this one actually is -2. Because if you go 208 minus 210, this is a -2. So this is somebody's thing that actually went up well. Oh, thank you, Lenovo. No thanks. All right, so step 4, we got part 4, 190 minus 188, which is a +2. So this person dropped theirs by 2 points. This person actually increased by a point, and this person dropped by 16 points. So out of these 6 people here, 4 of them went down. One of them only went down just by 2 points, and the other 2 people went up by 2 points. So I would say that this drug had 3 people effective significantly and 3 people not. Now, is that an effective drug? Obviously you'd kind of hope to have more than 6 patients, but maybe this was like hyper experimental, or this had to be done with a very small sample size. So step 2, again, we're going to assume normality, which is great because we don't then have to do a outlier check. So there's the assumption of normality, and now step 3, we're going to do, let me move down just a little bit more, so we can do steps 3, 4, and 5 all on the same screen. Okay, so now we turn on our calculator, we click on Stat, and we move over to Tests. Now, we are going to use the t-test right there. Now, before we do the t-test, we actually have to get the data into the calculator, so I'm going to click on the Stat button and click on the Enter button, and this is where I have to enter in the differences. So the first difference is 20 cholesterol points, and the second one 65, and the third one was -2. Be sure to use the negative key down here and not the subtraction key. Use the negative key. Calculator will not like you if you try putting in subtract 2 there. And then 2 is after that, negative, again by the decimal point, 1, and then finally 16. So there are our 6 data points. And then let's go back to Stat. Let's move over to Tests. Let's move down to t-test. Because again, this is one list of data. We took 2 samples, but now we've combined it into one list, so we're going to use the normal t-test. Now we're going to use data, and it looks like our mu sub 0 is 0. I mean, check it out, right? Mu sub d is 0, so mu sub 0 is 0. This is great. We could keep that exactly the same right there. The list is in list 1. The frequency is 1, and look at that. We want mu not equal to our null hypothesis right there. So again, we have, I know it's, basically taking that 0 and slapping it right there, but just match the symbol according to your alternative hypothesis. Okay, so now we're going to click on Draw, because Draw will basically do not only the t-value that we need, but also the p-value that we need and the picture. So it looks like my t-value is 1.6 standard deviations away from the norm, or 0 difference, and the p-value is 16.88%. Let's copy that down and get all the important information we need before we run our short analysis. So what we have here is the t-value, which is 1.6079. Our p-value is 0.1688. And our step 4 would be this beautiful t-curve here. T-curve based on degrees of freedom that we don't have to calculate. Thank you for the calculator. And we're going to plant our flag here at 1.6. So it looks like most of the benefit was positive, which is good. We had a lot more positive numbers than negative. But was 1.6079 strong enough to show us that we have a significant impact? And let's go find out. Let's see that 16.8% are your chances landing in these zones right there. Well, we tried our best because we gave alpha the best chance of giving us to reject the null hypothesis. We went all the way to 10%. So here we have 0.1688. Well, that was greater than 10. So this is a do not reject the null hypothesis. Do not reject. So our summary statement, which needs an inequality, since the p is greater than alpha, we do not have sufficient evidence to reject the null hypothesis. So do not reject the null hypothesis. Okay, now a fun fact though, if I decided that I wanted to go instead of a right tail, or a two tail, if I wanted to go one tail, that would cut the p-value in half and I would get a different conclusion. So you always got to be careful a little bit when you do two tails versus one tail. There may have been a benefit to that, but you know, I'm just giving you this one idea or thought about this. Okay, so on to the second and last example of this video. Let's look at the results from an obstacle course after an energy drink is administered. Assume normal distribution. So this is probably some energy drink trying to say people did an obstacle course and then we gave them our energy drink and then they improved based on that. That is a real faulty premise here to say that, you know, possibly practicing the second run through an obstacle course might actually be more impactful than drinking an energy drink. But okay, it is sketchy, but let's just kind of go through this example here. Because what it says, can it be concluded that there is a significant difference the second time, which is the after right here, okay? So what this means in my step 0, I've got to really figure out, like, okay, my null hypothesis, straightforward, easy to figure out. My mu sub d is equal to 0. Right. That means that you run the obstacle course, take the drink, run the obstacle course again. The drink had no effect. But the alternative is to say that the mu sub d, now here's the cool thing, like you can decide if you want the numbers to be mostly positive or mostly negative. And again, if you got the choice, let's make the differences between the after and before, let's try to make them positive. So what we want to show is that if your time went down between the before and after, we want to show that off as a positive number. So what we're going to do is, for step 1, we're going to subtract before, which should be bigger than my after numbers. Okay, now if we do this, we should see more positive than negative numbers. So here's a 4, here's a 5, here's a 3, here's a 4, here's another 4, and here is, a negative 7. So this person did a lot worse the second time, and so did this first person. Okay, so again, you should just kind of go through and think about, like, what order should you subtract. Now, if you did after minus before, you would notice that most all of these were negative, so you'd make sure that your alternative hypothesis was in a negative way. Now, step 4, or step 2, I have up in the problem assume a normal distribution. I put it in there. So we have no outlier check. This is really good. No outlier check. Assume normality. Okay. So we can assume normality here. And now we're on to step 3, 4, and 5 to finish the video. Okay, so let's see how we type this in. Okay, so we go back to our calculator, click on, click stat. Click, we got to enter the data, so stat and enter will get us to the data. Move all the way up to list 1. Okay, so now you see list 1 listed in this set right here. Clear the set by hitting clear enter, and now you can type in your new differences. So, -1. And we'll just keep doing this because the data list is pretty short. 2 enter, 4 enter, 5 enter, 3 enter, 3 enter, 4 enter, and -7 enter. So just go back and scroll up very slowly. Just make sure you typed in all the data correct. It's always good to check that. Then let's go to our t-test, stat, right, or you could have just hit stat left, and then move down 1 click to t-test, hit enter, and we have the data in list 1, so we want our mu sub 0 to be 0. Our null hypothesis is saying we're equal to 0. List 1, frequency 1, but we want right tail this time. And we're going to go down to draw because not only does this give us the t-value and the p-value, it also gives us that beautiful t-curve. So, looks like our t-value is 1.1708 and our p-value is a whopping 14%. So it looks like, despite the idea that this this t-curve right here, this normal t-curve, it's still 14% to land here in the shaded zone. See, our t-value was only 1.1708 standard deviations away from the norm, and so our flag is planted at that 1.1708 standard deviations away from 0, or the difference. And as we've learned in many, many videos, if you're 1 standard deviation away from the norm, you're still considered pretty normal. This is not a rare event. You had a 14% chance of landing inside that area, and I'm telling you, that's not rare. It's low. It is a very low probability. I mean, I would probably not gamble very often at a casino if this was your chance of winning. But this is definitely low. Whoops, excuse me. This is definitely greater than the alpha that we have chosen for this problem. And the alpha we have chosen for the problem is a very standard 5%. So this is do not reject, since the p is greater than alpha. We do not have sufficient evidence to reject the null hypothesis. So sorry, sports drink, you're not what's making the obstacle course easier on the people. So again, do not reject if your p-value is greater than alpha, which means that you had more likelihood of doing this than not making a type 1 error. And ladies and gentlemen, we are definitely going to not reject based on this information. Well, thank you for watching this, and we're going to have a part 2 to this video where I will not only do those problems that are very similar to the ones in the book, but also I'm going to do an outlier check for one of these as well. So stay tuned for the second video in our matched or paired samples.